Hello guys, welcome at MadMats Den. Today we will be talking about some hot topic, AI. So yeah, let's wait some time just to make sure one joins. Can you guys write anything in chat if you hear me? Okay. Then yeah, we'll meet a bit more to make sure if there's someone who wants to spectate my stream, he's gonna do it. And then, well, we start. In the meantime, I'm gonna entertain you with my jokes. Okay? Thank you for the awesome support, bro. So, how can you hear if you dare? Well, it looks like No one is joining, so I think we should start anyway. Are you okay with that? Okay, bro. Well, since we're still waiting for our only live spectator. Okay, I was about to start. Who? Can I use a Discord server of a friend to advertise my stream? You know them better than me, since probably it's you who made them. Yep, I'm talking about your Discord server, bro. Uh, okay. Ooh, we are two spectators. Welcome to the stream. Welcome, welcome back to Madmat's Den. If it's not your first time, otherwise, welcome simply. And I think now we could think of starting the heart of the streaming, let's say. So, What's wrong with my logo, LP? Just be quick so we can actually begin the stream. I just saw the screenshot you sent me. I don't see the second message. That's all, and I'm not gonna answer that because you. So, this video will be about a really hot topic: AI. So, what's AI, and is it really the all-knowing, all-doing solution to everything everyone treats it like? And what's the math about it? After all, we're a math channel, so yeah. So, AI is, first of all, an acronym: artificial, and that's given from the fact that's made on a computer. And then there's intelligence. So, the fact that this is artificial intelligence leaves us with the question, what is intelligence? Well, to answer this, we can ask ourselves what is not intelligent. And since we're talking about computer programs, basically, we can say that most computer programs should not be considered intelligence. So, what makes a program to be intelligent? Well, it's the ability of decision making. So, for anyone who has some knowledge about programming, he knows that every decision the program makes is based on some code we wrote. So it's we can say it's not actually the program that decides uh, what what he does. Otherwise, we would have a pretty random behavior, even when we don't ask for a pretty random behavior. So, how do we tell if a program is making some decisions? Well, this is a front that's developing more and more. However, for to evaluate decisions, planning is uh, a topic on which decision have to be made. So everything's everything for classical intelligence, classical artificial intelligence is about planning. So one might question themselves asking, what is planning? Well, planning is the ability to reach a goal given a starting position and some valid moves. So, in planning, we have, let's make a quick mind map. In planning, we have, of course, a goal to achieve. And also, we will have oh, some valid actions or moves. So, our artificial intelligence, when we ask it to move a coin from place A to place B, it doesn't tell us that the best way is to teleport it. Of course, we don't want that because it's not valid, it's not an option. And last but not least, we need an initial position. Sorry, more than an initial position, a current position, or status as it's called in AI. However, when lacking some kind of information or in a non-deterministic environment, this is replaced by a sorry, by a we can't have that, so we recur to a belief state. That's somewhat similar to a status in sense it guides us in toward a better decision. However, it's nested to other problems that makes us impossible to determine what's the actual state. So, first of all, we start with full knowledge, and deterministic, planning. This kind of planning is used, for example, when we are trying to make some routing on some graph. That may be some network or also traffic. We want to start at the starting point and end at some ending point. We have some places we can go to in various ways, and we have some times to reach a place from another given the routes. And this is an example of what we can do. So, for anyone having made a network course, this is a pretty easy to solve problem because you can use a Dijkstra algorithm. So, what's the problem with this kind of thing? Dijkstra also is complex when the number of nodes rises. And it grows like the square of number of nodes. So, what did they do uh, to make this uh, better to solve? I mean, not better on the way we are getting a really better solution, but we are accepting a decent solution without compromising the the time we need to use to solve them. So they switched to A-star algorithm. That is an evolution of Dijkstra algorithm. So what does A-star algorithm do to get a solution, not near necessarily the best solution, but faster? Well, uh, let's just compare the two algorithms. For both, lowest cost node is expanded. So we might wonder, what is the cost? And cost for a node in Dijkstra is literally cost to reach it. However, in A star, the cost is equal to cost to reach it plus estimate of the cost to reach the destination. So let's go back to the graph I had written here. And let's put some random costs around. 6, 2, 3, 4, 1, 7, 8, and 9. And also let's copy it on a new page. To explain how the algorithms work, we will have to name also the nodes. So this is A, this is B, this is C, and this is D, sorry. And I skipped this edge, so let's say this is a 5 cost edge. So let's analyze how the two algorithm works. So step 1, Dijkstra, and step 1, A star. So we need to say what heuristic we use to estimate the cost to reach the end. Let's say we just take the lowest edge, the edge with the lowest value that has not been expanded yet. So for now we have that the esteem is, oh, this node is not numbered either, so let's put 4 here. So I'm annotating the esteem to reach the end on every node. So Dijkstra S A B C D and E. Of course, at the beginning, so at step 0, we have that every node still keeping Dijkstra here and A star here, we have that the starting point for Dijkstra is cost 0. For A star, due to the esteem, is cost 2. We didn't have to do anything to get there, but we esteem that the cost to reach the end will be 2. Of course, we are making an assumption that will be terribly wrong. However, for Dijkstra, everything else is just infinite. And what about A star? Everything is infinite plus the cost esteem to reach the end. So we get this. Because we simply do not know how much it will take for us to get there. So we assume it will be infinite. At step 1, in both cases, they expand the starting point. So they get that A is 6, the cost to reach A. B is 2. And D is 3. B, C, and D are still infinite. What happens to our A star algorithm? Since S has been expanded, because we have that is it has the lowest esteem, we fixed its cost as 0 because we expanded it. So yeah, that's the real cost. We keep annotating that there is a +2, but we don't watch it anymore. On A, we have 6 plus 1, because we had already the esteem of +1 due to the distance from E, but we have also the 6 of cost to reach it. Then we see node P, and we see that there is 2 plus 2. And so, yeah, we didn't do much. C is still infinite plus 1, because we didn't reach it yet. And D is 3 plus 2. And of course, E is still infinite plus 0. So, at this point, we may notice that for both solutions, the first not expanded node is B. So, we go ahead with step 2. And for simplicity and avoid redundancy, we take out the already expanded nodes. So we have A to 6, B to 2, C, sorry, A is still 6 because 2 plus 4 is 6. And that didn't override the best path. D would be 7 passing through B. However, we had already a value of 3, so Dijkstra is keeping it at 3. However, we notice that C can now be reached with cost 3 again. And since we didn't reach E yet, it's still infinite. However, with A star, we get that A, of course, is always 6 plus 1, because as in Dijkstra, we didn't lower the... Sorry. Wait. The 6 of fixed cost is still him. However, the plus 1 will not be there because we defined as the non-expanded edge with the least cost, the esteem of the edges we didn't explore yet. So, since we chose B, B is always 2 plus 2 that is taken out because we are expanding it. There's no more point in esteeming. So C gets 3, D gets 3, and D gets infinite. However, now that we've taken out this node, this node, this node, this node, this, sorry, not nodes, edges, sorry, my bad. The next lowest cost is 4. So A had a distance of 1 in hopes. So the esteem to reach the end is 4. So 6 plus 4. D had 2, so plus 8. The end is always itself, so it has a plus 0. And C, it has a esteem of 4, of 1 hope that is plus 4. So, in this case, we will expand C. However, in Dijkstra, depending on the implementation, we can expand both of these. So, for Dijkstra, there are 2 nodes to choose from. So we'll need choose step 3 for Dijkstra. 1 assuming we use the C. And 1 is using D to expand. And here we will say step 3 for A star. And again, we will be taking out B because we already expanded it. So, if we expand with C, we have that A has a cost of 3 plus 4, and 7 is more than 6, so A will simply stay at 6. D, however, will be even worse because the next esteem will be 10. And yeah, 10 is more than 3. However, we will say an end that gives us a value of 3 plus 8, 11. Does this mean we terminate? No, because we still have d to expand. And on step 3 part D, we will have that A is 6 because it's not neighboring with D. C is 3 because expanding it from E, D will make it 10. So we keep it at 3. And that will be our best choice. D will be equal to 3 and we take that out because it's already expanded. And E will still be unreachable for us. However, for A star, we will have that we need to expand the node C. That means, of course, A and D are not expanded anymore. It's their values, sorry, are not replaced because, yeah, we have a cheaper cost to reach them. However, we will see that A is still 6, of course, and D will still be 3. E will, of course, be 11 plus 0. C, of course, will be 3 plus 4, but taken out. And what is the estimate of the cost? Well, we already took out 4 and this node at 4 and this node at 7 and also this node at 8. So for the two remaining nodes, we get 1 hop times 9, that is the only missing edge, so plus 9, and here plus a whopping 18. So we terminate. Now, what happens instead in Dijkstra? Well, we already said it. We will need more steps. Quindi step 4C and step 4D. So here we will just see that we can try overriding C with a higher value. However, we already took that out, so D doesn't reach any node, so yeah, we still get A equals to 6, that will be chosen. D equals to 3, that is expanded now. And E equal to 11. That will be a value to check if it's right. For the D version, we will have A equal to 6, because, as always, 3 plus 4 is more than 6. C will be at 3 and expanded, so taken out. And D equal to 11. And now, always, will be considering A. So we will need a step 5 that will be reunited from both of them, in which we say A as cost 6 and will be expanded, and D, since 11 is less than 6 plus 9, 15, will be equal to 11, so they will both terminate. So, This simple estimate of the cost needed to reach the destination allowed us to simply discard analyzing some paths that were obviously uh, of higher cost and focus on the path that promised us to get there faster. And once we did all the calculations, we get we got the new new value in a saving two whole steps of expansions. And this is the reason why A star is much more used than Dijkstra in many situations. So, someone might say, well, okay, so now we solved the routing, so that's AI? Uh, kinda. I mean, this is a possible usage of AI because actually we use these heuristics to promote something that an exact algorithm would forbid us to prune away and yeah, focus on tell us to focus on something more promising. So Dijkstra algorithm uh, is an algorithm that allows us to uh, compute with exact the best route possible. A star, given the exact heuristics, will give us the best solution. However, it will make us save time because their decision making is better. Yeah, it's like saying on it's like we can say a computer, hey, yeah, you have 50 paths to uh, get me to another point. How and all the paths are linked between them. But you know what? If you just try to expand going from a path to another instead of following it, you will probably lose some time because, yeah, you are not going in the right direction. So, this is the first thing we can say about AI. It's decision making that's deeply rooted in yeah, distance from the goal. You estimate and try to check if the estimate was accurate. So if let's take ourselves a bit of break since I just dropped a bomb in calculations and the concepts. So yeah, I'll go drinking something. I recommend you to do it too. And let's see ourselves here in, let's say, 5 minutes more or less. I will check if you are back before continuing. Don't worry. See ya. Of course, if you have any question and didn't leave the stream to have your break, you can ask them in chat. Okay, guys, so are you back? Sorry, my bad. Okay, so Elpideus is back, and what about Robbie? Or if someone else joined the stream, please come say hi in the chat if it's not Ruby and she disconnected, or he is not Ruby if she disconnected. Well, since how much math I put in that, I suppose 5 more minutes of break wouldn't hurt. Am I right? So, I think it's time to make a presence check. So, Elpideus is here somewhere. Okay. Rubireva is here somewhere. I suppose it's a no. Is there anyone else I don't know about somewhere? Then why did absent people never answer my questions? Do you have any clue, Elpi? Okay. So, we were saying that thanks to heuristics, A star is a bit more free to go in smart directions when uh, going towards the end. Does that mean it's actually AI? Well, not really. I mean, it's still a traditional algorithm. It's closer to AI than other algorithms in the meaning he used heuristics, and I needed it uh, to be said because we needed an heuristic. However, no, it's not that. It's not an AI. So let's say instead that instead of this graph, knowing we start from here, let's say we have the correct cost of each node. So let me uh, see if I can copy again the. Okay, no. Let me copy the clean graph here. And let's add again that 5 and 4 I had missed out on in the first place. I can't find my pen. Where did I put my pen? Here it is, my pen. So here we had a a 5 and here we had a 4. And this is a node like everything else. And this is our end node. Or so it's our goal to go here. And let's say we can calculate easily the cost from to reach every node from our end node. So yeah, we can say this is uh, 14, 11. Okay, so how would an AI behave if it is on a graph like this, and to have the AI to act, we don't need to analyze her actions uh, in this instant way. We say she can only see her node. For this example, we'll pick this one as start. She can see the costs of the edges and the stem of the distance of the nodes from the end. So, what would an agent probably do? Well, it will see, well, the cost on the node it's on, it she doesn't care actually. So yeah, she will say, well, I can have a 2 cost path to a 11 cost node. Okay, seems legit. Then we have a 9 cost path, a 4 point path to a 9 cost node. So 13 versus 13, they seem both good. We have a 5 cost path to a 14 cost node. Ew, 19, bad. Let's discard this solution. And then we have a 1 cost path to a 8 cost node. Yeah, let's go like this. So, now we have a new place. And so we have a 7 point path to a 14 point node. Pretty horrible, knowing we're on a 8 cost node. So yeah, let's not talk too much about that. We have a 1 point path to a 9 point node. So we can definitely give up on that node. And of course, when we saw this node, we could give up on those. Otherwise, we have a 4 point path to a 9 point node. We have already a better esteem, so yeah. And a 8 point path to the end. Of course, this is the best. So, this is what AI agent would look like in doing this stuff. But, is this an heuristic? No, we just calculated the node of the cost of the node. So, yeah, it's not much like that. Let's say, well, the AI can't see everything that well, so let's say he didn't calculate it like this. However, she made a more approximate cost to lower down the cost in case of need to explore the graph. So, what would costs that actually make sense to an AI be? For example, we could choose again the lowest edge available and multiply it by the distance to reach the end. Would that be good? Absolutely not for an AI like this. So, what would be a better esteem? Well, simply, let's take, for example, this time, an average. And when we talk about heuristics, there is no answer that answers all questions. Every time you use heuristics, probably you'd have to uh, search one that is good for the situation. Or if you don't want to do that kind of blind search of the heuristics, it's much better to combine multiple heuristics to get heuristics that has more or less the good stuff from everything. So let's say that is 5 times the distance is in hops. So yeah, basically this would be a much more realistic uh, coin cost esteem. So what would the AI think? Choose to path to reach a 10 node. Okay, seems pretty high since we already did it. So let's discard this one. It's simply too high. 5 plus 10? Of course not. 4 plus 5 going toward the upper node? Well, some AI may think, well, we didn't have anything better until now, this is better than our Steam, let's take this. Some other AI would say simply, okay, this is a feasible result. However, let's explore more. 1 plus 5. And for example, the AI that need to operate on very large spaces will stop probably at the first good value. Or even sometimes will accept to worsen their value, but just, yeah, try to find a better solution passing through worse ones, even if it doesn't make much sense. However, since this is a little graph, we could say, yeah, let's go here, in the 1 plus 5 after having analyzed all the possibilities. What are the chances now? 7 plus 10? You. Bad, it's over 3 times the expected cost from here. One plus 10? A bit better, but not that much. 4 plus 5? Wait, was it 4? Yeah, 4. Well, maybe. I mean, the cost of the other node purely is good. However, we also have 8 plus 0. Hey, here is the end. Let's go eat here. And that's how an AI would work. So, uh, we had seen before that the minimum cost was 9. And what cost did we achieve? 9. So, yeah, here I used a really weird and somehow raw heuristic. However, if you have very many nodes, you can just, yeah, find a better heuristic. And, yeah, make a good estimate of how much it takes that to that node. Maybe a better heuristic for a really much larger graph would be for every node going from the end, saving number of hopes and I don't know, maybe uh, taking 7 out of 8 from the previous node from the value plus 1/8 of the edge value. That way we have an estimate of the average cost of every single step to go to the end. And like this, we have a pretty much raw, still better estimate of how much the the path will be. Otherwise, instead of using these fixed values, we could say n minus 1 over n, in which n is the number of hopes, and also add 1 over n times the edge value. This way, we will have a very better estimate of what happened to everything before. Of course, these heuristics would need a stronger computational power than putting 7, 8 and 7 over 8 and 1 over 8. However, yeah, when you talk about heuristics, you have to make a simple choice. Slow but good. But good. And these are the one mostly wanted in optimization algorithm. And the raw but fast heuristics that are usually in AI. And that's for a simple reason. If you are using an optimization software, you want something that is close to the best. So here you care about the goodness. However, in AI, often we are looking more to a immediate response or however fast response. So yeah, in AI and optimization, you use different kind of heuristics, but because you want to have different kind of results. In AI, it's inconceivable to simply stay there calculating more and get closer to the optimum. However, in optimization, that's the whole point. You want to get as close to the optimum you can be. However, I forgot to tell, this was is called local search, because simply you export the neighbor and try to find the best. And most of the times, uh, you ignore maybe the edges because you take something like the heuristic we said before. So you just scrap the edge value in the value of the node. So yeah, you simply go toward the goal without thinking too much about the cost. So yeah, for the first heuristic I used, that was 5 times the distance in south. From here, it was pretty weird. And also, taking 8 as a denominator here would have been a pretty bad result because, yeah, it's too small of a graph to use that scale. However, yeah, to make an example, it was, I don't say it's good, but it's practically acceptable to make an example. Yeah. Also because when you go to from having uh, that few nodes to having a 9 by 9 matrix of nodes, actually you will need to uh, find a fast way to find the heuristics. Also, if you go onto something not as huge but still pretty complex, like a node like a graph like this. And here you can't give a fast solution if you simply accept to calculate like everything. Yeah, this node, this time everyone would use pretty much raw heuristic to solve, because simply, yeah, it would be a suicide on performance to try and find a really good estimate of the results here. So the 1 over 8, the heuristic in which node cost equals uh, hop number times uh, 7 over 8 previous node value uh, of this plus 1/8 of edge cost would mean, yeah, let's say, for example, that going from the end towards other stuff, the cost of the nodes are these to make it simple. So this is 1, this is 7 over 8, and this is 3 over 4. So now we have 2 hopes plus 7 over 8 plus 1. So it's 15 over 8, 15 over 4. Okay, 15 over 4. And going on like this, you get more or less an idea. So yeah, by the time you reach here, you would have had a lot of calculations, and simply this heuristic would be like a pretty fast heuristic to calculate if you save for every node as a pair and compute later the actual cost to use for the path. So yeah, it's much better to do this than uh, than everything else, and so you can launch fastly the local search. That will simply be good enough to reach the end. Welcome back, bro. So yeah, I just said, yeah, this is, sorry, this one was called the local search, and also that heuristic are split in slow but good heuristic that are used in optimization, and raw but fast heuristics that are usually used in AI. Because in AI you want a fast solution, and in optimization a good solution. And in AI you don't care about too much about how good it is, while in optimization it's the whole point. As in optimization, yeah, you don't care too much about the time needed, as long as it's acceptable, at least polynomial, since most problems you solve with optimization heuristics are NP-hard problems. So yeah, stuff that has exponential time cost on the number of nodes in the instance. So yeah, since local search gets stuck on local minimum, because simply it tries to lower the value. And yeah, I have this value, and everything near this is higher, so I don't know where to go. And this would stall the algorithm if you're trying to reach a certain value at least. So yeah, uh, there for this reason, various mechanisms to avoid local minimums or get out of them have been implemented, and since this is a problem for both optimization and AI, they both came up with some more or less complex solutions. And of course, the most complex ones are in optimization, since it gives a crap about the results more than about time to compute them. So yeah. However, I think this would be a good ending point for today's stream, and in, I think in the next video of the series, I will in the next stream of the series, sorry, we will start discussing adversarial planning, or maybe I'll let you decide if you want that, or maybe online search. That is uh, that also requires not complete information. So yeah, I think I'll make the spectators of the next live choose. So don't miss the next live, and see you guys.